Chapter 11, Design of Beams and Shaft, example number 2. In this example, we have a loading like a concentrated load applied at the two simple support beam like figure below, and a distributed load varying from 0 to 5 kilopound per feet on the other side of the structure. So if we want to have the lightest weight wide flange beam, we, when we know the sigma allowable is 24 ksi and tau is 14 ksi. So let's start our problem. So in such problem, we do need the section modulus, which is maximum over sigma allowable, which is provided in problem statement, and maximum we need to go through the shear and moment diagram and get the maximum moment possible. So if we want to draw the shear and moment diagram, first of all, we need to calculate the reaction at A and B. So for doing so, for example, summation of moment about point A, which is here, goes 0, like it says 15 kilopounds times 6 counterclockwise, which is a positive direction, minus if you just convert this the distributed load to a concentrated load, that's the area under loading, and that's 22.5 kilopounds, and make a negative because that's a clockwise, the moment times distance, which is 1/3 from base. Base is 9 feet, 1/3 is a 3 of that, plus RB times the total length of 9 feet. If you do the math, it just gives you RB. Reaction at B is a negative 2.5 kilograms. As soon as we have reaction at B, summation of forces should cancel out the reactions, should cancel out the forces. So a 2.5 downward, a negative 2.4, another downward, 25 plus 15, 40 RA is 40. So we just came down by the amount of negative 15, no nothing to disturb us from here to here. Then all of a sudden a upward push equal to the reaction of RA, which is 40. Then if you just take the 40 here, negative 50 plus 40, that's a positive 25. Then the amount of load is reducing. It says the shear, the slope of shear diagram should decreases until it reaches to 0 for load. Then a horizontal line has a slope of 0, and it's not coming all the way down because the area under here is 22.5. If you subtract that from 25 over here, just gives you one extra 2.5, which the negative direction for RA is responsible the same amount, but in the different direction, it just gets us to the origin. If we want to draw the moment, so area under shear is moment, 6 times 15 is 9 negative 90 down here, and the other part, the numeric value of RA of this part is of shear is reducing, so the slope of moment is reducing until it reaches to 0 at the end. So the maximum moment is already calculated to be negative 90 because the rest of the point are something like top of that, about that number. So when we have all the material, we can just replace all moments, forget about the direction, 90 kilopound feet converted to inches over 44, which is a sigma allowable, that's 24, and it just gives us S, modulus of section. Modulus of section is equal to S of 45 inch cubed. Then as soon as we have S, we need to jump to the table. So if you look at W16 times 31 has the S equal to modulus of section of 47.2, which is a good estimation of that. So if you just consider you are selecting section 16 by 31, which has the Sx is equal to 47.2, B is 15.88, and TW is point. Inches. DW is 0.2775 inches. As soon as we have our section, we can check the shear stress over here. If you just check the shear stress, you just need to the calculation for tau max, and that's V maximum over the area of web. And if you just look at the W16 times the TW times web is 9.12, then no, my bad, that's the total area. So if you just take and V maximum is 0.5 positive 25 over a E times T, and it just gives us 5.72 KSI. It should be smaller than our allowable tau. Thank you. So we can easily choose or select our section by white flag 16 times 31 by Sx of 40 modulus of section of 47.2 inch cube, depth of 15.88, and a thickness of the, let me get rid of this one, thickness of the equal 0.275. Thank you.